Thank you so much, Jules. And quick reminder once again. So if anybody want to tweet about this talk, please use the hashtag PyCon JP_4. And Jules Poon, the stage is yours. You can start with your presentation in a minute. You can start.
Okay, hello everybody. So I'm Jules, and I'll be presenting an overview of the optimization pipeline in CPython 3.13 and some work Kenjin and me undertook last year. So before we start, here's a timeline of roughly what happened. Before me and Kenjin started university, Kenjin was already part of the effort to make CPython faster. In early 2023, he approached me to collaborate to experiment with some ideas for making CPython faster, and we wrote 2 experiments for it. At the end of 2023, though, I dropped out of the project due to personal health, and Kenjin continued to write the final version of the optimizer that is now in CPython 3.13. So today, I'll be presenting on the first experiment, implementing a technique called lazy basic block versioning, where we incorporated a copy and patch JIT compiler. And this was mostly an academic pursuit for us to experiment with various optimizations and discover challenges associated with our goal. Next, I'll be presenting on an overview of the massive amount of work by a lot of people that has ultimately gone into CPython 3.13. So before I get into the details of the optimizing passes, we would like to establish some background about CPython internals. So if you didn't know, CPython is a reference implementation of Python. If you installed Python from the official website, you're probably running CPython. And the C in the CPython is a reference to how CPython is written in the C language. Oops, yeah. All right. So CPython is what we call a bytecode stack machine. Bytecode refers to an instruction set that's designed for easy interpretation. And you can think of the bytecode as a sequence of instructions that the interpreter runs. And the reason why bytecode exists is because it's way easier for the interpreter to interpret bytecode than to execute your Python code directly. So the reason why CPython is called a stack machine is because it uses a stack to store its intermediate results. So I think it would be helpful to run through an example. So let's say we have the expression over here. It gets compiled to this following bytecode. And let's step through the execution. So you first load 2 variables, A, B. Then binary op over here would pop the 2 values from the stack, and then it pushes the result up. So this is what you get. Then we can do the same for the next binary op, and the result is left at the top of the stack. So if you notice the bytecode is generic, that means that it works for all types of values. In our case, A, B, and C can be a string, integer, or float, or even an object. So for each type, the bytecode has to perform something different. This means that some of the bytecode, in this case binary op, has to perform type checks and dynamic type dispatch, and so this makes it kind of slow. A major change in CPython 3.11 that made things faster was a component called the specializing adaptive interpreter. This component observes the types a bytecode encounters at runtime in its input stack variables. If a bytecode consistently encounters a certain type, it rewrites itself to a faster version of said type. In other words, it kind of like specializes for the said type. This allows a specialized bytecode to avoid unnecessary computation for having a generic object, and this makes it faster. And this specialized bytecode is often referred to as the tier 1 bytecode, and we'll be using this terminology in later slides. The tier 1 bytecode might also cache intermediate computations to avoid expensive recomputations, such as expensive lookups like getting an attribute. So in this example, let's say A, B, and C are consistently integers. Our binary op was specialized into the following that handles specifically integers. And load globals will be specialized to this, which takes advantage of some form of caching to avoid looking up the globals again. So this often produces quite a significant speed up in cases like calling a Python function or loading an attribute. If you want to know more information, you can view Brent Butcher's talk from last year about the specializing interpreter. So to recap, here's where we are. The CPython compiler emits tier 0 bytecode, which is like the normal bytecode. And then when it gets hot, it overwrites itself to a more efficient instruction we call tier 1. So now I'll be diving into the first experiment that me and Kenjin did. When we started this experiment, we did not really have an idea of what the CPython optimization pipeline was going to look like. So our goal was simply to do something with tier 1 specialized bytecode. we chose to experiment with lazy basic block versioning, and we call this fork of CPython PyLBBV. So lazy basic block versioning, or LBBV for short, is a novel idea by Maxime and Mark to remove the overhead of dynamic typing for JIT compilers. A very, very brief summary of the idea is to insert explicit type checks into code, and we'll subsequently call this type guards. And based on the runtime type encountered, lazily generate optimized bytecode. Optimized basic blocks specialized to the encountered type. So, yeah, in order to incorporate this idea into CPython, we had to introduce a new class of instructions that we call tier 2 instructions. Later on in CPython 3.13, a similar construct will eventually be called microops or uops. The tier 2 instructions, in order to support LBBV, we had to break up a tier 1 instruction into smaller instructions, and this helped us to identify repeated work and to eliminate the repeated work. We also had to add explicit type guards and special branching instructions to support lazy basic block generation. In addition, we also tried to support float unboxing, so some instructions were added to do that. So tier 2 gets triggered when the code gets hot, and tier 1 has already been triggered. So it's a bit hard to describe it abstractly, so let me just step through a simple example. Suppose you want to execute this Python source code, and we first warm up the code, warm up the function f by calling it 63 times, and then this triggers tier 1 specialization. And then if you were to call it the 64th time, it triggers tier 2. And so let's step through like how tier 2 works, or in this experiment. So at first, we don't have nothing to execute, as the tier 2 code generation has not done anything. So I'll use the blue pointer to represent the code gen, and the orange pointer to represent what has been executed in tier 2. So first off, the code gen looks at what tier 1 bytecode needs to be executed and emits the corresponding tier 2 bytecode. But as it emits, right, it will have to type propagate across that instruction. And this is for later on when you want to do certain in order to detect repeated work done, we have to type propagate each emitted bytecode. So we continue this for load fast, and so it emits 2 load fast until we encounter a special instruction, which is a type specialized binary add. For this, we had to emit a type guard, which checks whether the first variable, in this case int, in the case is the letter A, whether it's an integer. And we need to emit this guard is because the type propagator has no idea what type A is. Then we emit an instruction that handles lazy generation. Then we run the tier 2 instruction up to the branch instruction, and then this triggers the lazy generation of the next basic block based on the result of the type guard. So first you have to update the type context based on the result, the runtime type, which you know is an integer. Then we also need to do it the same for like the letter B. Then since at this point right now, since we know the types of both A and B, based on the fact that both guard passed, we can just emit the binary op add in rest, which is an instruction that does addition without checking the types at all. So here, sorry. Then we can do the same for the second op, and then if we load the next operand, you can see that on the stack right, we have integer, so we don't need to emit any more checks, and we can just emit a type specialized operand that does not do any checks. So in this case, we have eliminated 2 type checks compared to the tier 1 specialized bytecode. Then we can finish the code gen and continue execution. So if you run the function again with the same types, it doesn't need to generate anything because the basic blocks has been generated already. So let's say we run with a different type. So things happen the same way until the guard fails. In this case, because the guard fails, it prompts the next instruction to generate the next basic block, which is specialized to floats. So we have to we do the same thing, and then we generate a new basic block specialized for floats. Yeah, so what we get from this is we get, of course, guard elimination. And I think we also get, so the thing is that we also get free date code elimination because it won't generate basic blocks that doesn't get executed. And we also get free loop unpeeling, which means that we can exploit type stability in loops even if the initial iterations are not stable. So when we wrote PyLBBV, we encountered a problem, which is that At that point in time, CPython had 207 instructions, which means that manually writing the type propagator would be extremely tedious. But thankfully, right before PyLBVV, a domain-specific language, DSL, was introduced to specify Python bytecode interpreter semantics. And so our solution is to simply extend the domain-specific language to specify also the type propagator semantics, and then we can generate it automatically. So I'll skip through the example. And when we wrote PyLBVV, we realized that it was actually really difficult to support all of Python. And a lot of eventual work on UOps in CPython 3.1.3 was not done while we were writing PyLBVV, which means that when we were writing basically a sheet here and a lot of the eventual micro-ops, a lot of our analogs were kind of ad hoc, and there were a lot of annoying edge cases as well because we were working with a tier 1 bytecode that was not meant to be split into UOps. So for instance, like we had to deal with instructions with runtime dependent stack effect, which means that we cannot type propagate across it properly. So unfortunately, the results for the experiment was horrible. And I think there are a few lessons to be learned from it. So while we achieved like a 40% speed up arithmetic, there was 0 speed up anywhere else. This is probably a lot of reasons. For instance, like it could be because, it's probably because there were a lot more instructions executed and there was no way to like remove that. The optimizations were not strong enough to remove the overhead. Also, like we did not support a huge portion of Python, so we couldn't profile it properly. And we later slapped on like Brent Butcher's copy and paste JIT compiler, and it actually achieved a slowdown. And I personally think it's because the basic blocks in our version was too short for the JIT to be helpful. So now I'll be covering the eventual work that went into CPython 3.1.3. Unfortunately, at this point, I was kind of like not very involved in the project anymore, but I'll still present it because I think it's the part where most of you are here for. So, and it's really a lot of work that went into this, which I was not very involved in. So in 3.11, right, remember the specializing interpreter. Bytecode optimizations only occur across like 1 or 2 instructions, where it rewrites 1 or 2 instructions. In 3.13, though, the optimization take into account larger regions of code, allowing us to use more information about the surrounding code to make more ambitious optimizations. The key observation is that, which also other language runtimes realize, is that you can use the types you learn at runtime to do larger region optimizations. This was not a new idea. This was pioneered way back in the Self language, and is commonly used in JavaScript and in other implementations of Python like PyPy and Psycho. So this is not a new idea at all. The tough part is implementing it correctly and safely in CPython while also not increasing maintainer burden. So as you know, CPython 3.13 currently ships with an experimental JIT, and the JIT with just-in-time compiler. The optimization pipeline is shown over here. CPython currently does not build with the JIT on by default, and while it provides speedups in some applications, it slows down many others right now, in addition to taking up more memory. So a lot of stuff is currently work in progress and will only appear in CPython 3.14 and onwards. Yeah, so here's the overview. So you first start with like CPython tier 1 bytecode, and then it goes through this component that projects traces. And the resulting trace consists of micro operations, which is UOP trace. This UOP trace passes through a trace optimizer, and the optimized trace is then passed onto the JIT compiler, which produces machine code to be ran. So after experiment 1, I'll go slowly morph along with other developments into working on the trace optimizer, and this is the part where I'm most confident presenting. So the entire pipeline is often called just the JIT, but which is the case for JITs in general. But this is a bit of an unfair generalization because JIT compilers have multiple separate parts that can differ between implementation and usage. People often think of like the JIT as like a magical solution to make things faster, which is not true in general. So for CPython, as we've seen in our first experiment, where we throw in a JIT and it actually made things slower, for CPython, right, these 2 components are absolutely necessary for a chance to make it faster. So now I'll be talking about the first step in this pipeline, which is projecting traces. As of right now, if you build CPython with the JIT compiler, it would try to like predict a trace. So traces are just like straight line code sequences. There are no branches in a trace such as if-else other than a jump back to the top. This is because the projecting trace step only predicts one path. So we start the trace from the backward edge of a loop. And then as the trace records execution, right, the specialized bytecode gets broken down into smaller units, which we call micro-ops. This is kind of similar to what we had in PyLBBV, but a lot more comprehensive. As before, these micro-ops allow us to identify repeated work across multiple instructions. In this case, for iter range gets broken down into the following 3 instructions. And the trace, in this case, continues to be executed, continues to be predicted until the trace stops here. And usually the trace stops when there's a backwards jump or it becomes too long or unwieldy. Yeah, then there's a trace. So then these traces will pass through the trace optimizer. Here's the overview of the optimization step. It is planned to be consistent on multiple passes, but only cover the current tool that's currently in the CPython code base. The first pass is written by Mark Shannon and already implemented in CPython 3.13. It promotes constants to globals. And so the objects the trace access in the global scopes gets burned into the bytecode, making global lookups a lot cheaper. The next pass contains stronger optimizations. So this pass was written by Kenjin with help from Mark Shannon, Guido, and Peter. The current plan for this pass is to perform guard elimination, true function inlining, deferred object creation, and register allocation or top of stack caching. So the main analysis that enables this optimization is an abstract interpreter that has already been implemented in CPython 3.13. As of CPython 3.13, the guard elimination has been partially implemented, and the rest is planned for CPython 3.14 and beyond. So, as I said before, CPython's data flow analysis uses a technique called abstract interpretation. For those who don't really know what abstract interpretation is, in normal interpretation, you interpret bytecode and the values you operate on are Python values and objects. In abstract interpretation, you still interpret bytecode as usual, but operate on abstractions of Python values and objects. So in CPython 3.13, the abstraction is mostly the type of the object. And now it faces a similar problem to PyLBBV, which is that we need to maintain 2 largely disconnected interpretation specifications, which is extremely tedious to maintain concurrently. The solution is, again, to use the domain-specific language to specify the abstract interpreter. So here's what is in 3.13. The vast majority of the abstract interpretation pass is automatically generated. In CPython 3.12, the specification bytecode.c is mainly used to generate the interpreter. But in CPython 3.13, the bytecode.c specification is also used to generate majority of the cases for the abstract interpreter. And special cases are handled with a relatively small and easily maintainable specification, optimizer bytecode.c. So now let's look at the guard elimination. To recap, every time Python executes specialized bytecode, it needs a guard to check if the types match or if our assumptions hold true. These are usually very cheap, but if you can eliminate them, let's eliminate them. So for this optimization, we use the abstract interpreter to keep track of what variables we know the type of. If it sees that we already know the type of something, we can eliminate the guard. For instance, after the first type check, we know B is an integer. So the next type check over here is not needed anymore. And the last type check is then converted to a cheaper one that only checks for the variable A. More information is propagated as of now, not just types. A limited form of constant propagation is also done. For now, it just propagates Boolean constants. But in the future, bigger constant folding stuff might happen. So the next optimization in one is true function inlining. This was worked on by Kenjin, but then it is put on hold for now. The idea is that essentially every time you call a function, there's some overhead involved. And to reduce that overhead or to remove the overhead, you can manually copy the body of a function and paste it into your code, but that's not very clean code. So instead, the optimizer tries to do that for you within the trace. So here's the ideal example that we hope that will happen. Here's Python code where f calls g in a loop, and the resulting trace contains both the body of f and g, including the pushing and popping of frames. So frames in Python are used to keep track of a call, stuff like local variables and constants. But this is also where a lot of overhead lies. So the idea for this pass is that if the frame fits some predetermined guidelines, what if we can remove the frame altogether? And this removes stuff like the overhead of creating a frame and copying your arguments to a new frame. Kenjin thinks that this could result in roughly a 30% reduction in function call overhead. And he thinks that with more optimizations, the overhead of a call through Python could be almost as low as calling a C extension function. The next optimization is deferred object creation. This is Mark Shannon's idea. I'm not particularly familiar with what the plans for this. But the main idea is that we can defer the creation of an object or not create the object at all in certain cases. So for example, if you have the first example, right, what if you can return a tree without ever creating a list? A more powerful form of constant evaluation would be able to do that, probably. Another example over here, you see the filter. What if the initial list is not even created? So the next pass is register allocation on top of stack caching. This is going to be worked on by Ben Butcher. So recall that operands in CPython bytecode is stored on the stack, right? But stack resides in memory, and there's a lot of overhead when you read and write to memory compared to like reading and writing to the machine registers. So what if we want to remove that overhead? So what we can do is that we can cache the top few values of the stack in registers instead, and then in order to keep track of what is the top of stack, we can use a stack machine. This could probably net us like single-digit wins on some benchmarks. So the last part is the JIT compiler. This part was already covered in a talk in PyCon US 2024 by Ben Butcher. You can watch the recordings uploaded onto YouTube. The main idea for this trace to machine code compiler is to create a bunch of like machine code templates for each bytecode with holes in them. So how you compile a trace is for each bytecode in a trace, you copy the template for each bytecode and paste it into like a memory location, and then you fill up the holes. Then you can just run the whole thing. So this is a very simple idea. It does not need CPython to package a large dependency like LLVM to perform JIT compilation. So that's all for the pipeline. At this point, like you might be wondering, like, okay, if a guard fails or the runtime is like wrong and the trace like is wrong, like for instance, if the trace is optimized for integers but you see a float, then what happens? So in the happy path, we can assume all kinds of things that the runtime do and do all sorts of awesome things, but we still need to check whether assumptions hold true. And if assumptions are false, we reconstruct the entire state of the interpreter and exit out of the current trace, either to another trace or back to tier 1. So there are two kinds of exits, side exits and optimizations. So for side exits, these are fairly normal events that happen, and we might want to create another trace from the side exit. So we'll first jump back to tier 1 if the side exit happens. But if the exit is taken enough times, a new trace will be created. So for example, if the following function creates a trace, assuming its inputs are integers, if you then pass in a float, the next time you call the function, this guard, the guard top of stack in will fail. That guard will fail. And so it will jump out the trace, and if that jump out is enough, you'll just create another trace that is specialized for the new types. For a de-optimization event, we will drop out the entire trace and back to tier 1, and this is a generally pretty rare event. It's a pretty rare event where we don't want to create a new trace. Yeah, thank you.
We have 10 more minutes of time. Anybody have any questions? Okay.
Thank you for presenting on a very interesting topic. My question is, historically, the Python interpreter was designed to be simple enough that any motivated grad student could figure it out. And all of the optimizations that are being added are making the interpreter much more complicated, to the point where even I, who could read it 3 versions ago, cannot make sense of it. At what point is the complexity of these additional optimizations making it too hard to create, find, or train new CPython developers who can actually maintain them?
Sorry, can you repeat the last sentence? I didn't catch it.
At what point are these optimizations going too far, making it too hard for people to understand what the interpreter is doing and making it too hard to find or train people to maintain these optimizations?
Okay, so I'm probably not the best person to talk about this because I'm not very involved in their decision making. But from what I understand is that like the entire tier 2 stage is fairly transparent to tier 1. So people who maintain like other parts of Python need not know anything about the tier 2 interpreter.
Any more questions? If there are no further questions, we'll just stop this presentation here. And thank you so much once again, Jules, for providing an insightful talk. Give her a big round of applause.